Hello and welcome to this video lecture. For this lecture, we will discuss, now for the first time, second order systems. So up until about this point, we've really just been thinking about first order systems. So now let's build on that discussion by increasing the order of the system and consequently increasing the order of the differential equation. So this discussion will be a bit on the limited side in terms of applicability for differential equations, because we're just going to work with essentially, and we'll get this in your notes in a second, but essentially second order LTI systems, linear time invariant systems. Initially, we're going to just discuss homogeneous systems, and then we'll get into non-homogeneous cases later. So if you recall, the general form of a linear, homogeneous second order ordinary differential equation, otherwise known as LTI. Oh, well, I have to get in with constant coefficients, then I can say LTI. So here we can abbreviate that a little bit more succinctly as a second order homogeneous LTI differential equation. I guess we could include ODE. So the general form for that kind of equation is, and here I'll go to the dot notation where the dots represent derivatives with respect to time, as you probably were exposed to in your dynamics days. So we'll have x double dot plus ax dot plus bx is equal to 0. And you might be saying, well, Professor Densmore, what happened to the possible leading coefficient for the x double dot term? And of course, what have I done? Since this is a homogeneous equation, I just multiplied the entire equation through by 1 over that constant, making the coefficient for x double dot unity. And then, of course, the other constant coefficients then just became different constants. And in the end, we would just combine all those constants together, and in this case, we would call the first of those coefficients, first of those possible non-unity coefficients A, and the second one B, and of course, none of that affects the side that is equal to 0, so we don't even have to worry about that. So this is a general form, just we've gone ahead and simplified that form just a little bit. So now let's go ahead and assume. So let's say that maybe we can guess the solution associated with this particular type of differential equation. And again, remember, the whole point of classifying differential equations is so that we can apply a particular solution framework. So for this second order LTI ODE, we're going to assume that we have a solution, and let's go ahead and borrow from our first order LTI differential equations and say that the solution has the form e to the st. Because if you recall, if we have a first order differential equation, first order homogeneous LTI ODE, we found that we could separate variables, and once we separated variables, the solution had a form, a general form of e to the something, e to the something times t in this particular case. So why don't we just go ahead, if that was a good solution for first order differential equations, maybe it's a good solution for second order differential equations. So let's go ahead and just give this a try and see if it works. Now, of course, since I'm spending time lecturing on it, what does it mean? It means it works. So let's go ahead and then capture, of course, our derivatives. And so the whole point of this lecture is to show you how it works and to show you the very interesting things that we can conclude about these kinds of second order homogeneous LTI ODEs. And so it's pretty impressive what you can deduce from assuming this kind of solution. So we have our derivative chain. So we start with x. We have assumed a solution. So that means that we have also bought ourselves a specific set of derivatives. So for x dot, we get that being equal to s times e to the st. And x double dot, we have s squared also times e to the st. So going ahead then and substituting into our differential equation, we then get s squared e to the st plus a, not two a's, as e to the st plus then b e to the st, because remember x was assumed to be that initially, so that just comes in for x. And of course, that whole thing is equal to 0. Now, we can then, since clearly each of those terms on the left-hand side has one thing in common, specifically e to the st. And so you can start to see how interesting this is. We get s squared plus as plus b times e to the st is equal to 0 for this particular, or for this specific assumed solution. Now we can draw some conclusions though. And just as a little bit of a note, this is going to be one of several approaches that we develop for handling these kinds of differential equations. So I don't want you to think that this is going to be, and this is the one and only way of working with these kinds of differential equations. There's multiple ways of doing it. But this leads to some very interesting concepts that we can use not only in this approach, but also in other approaches. So let's go ahead and press through this development, and then you're going to see me develop a slightly different way and then another slightly different way before we kind of call this general discussion for this class of differential equations done. So let's go ahead and press forward though, because we have this particular relation that we can deal with, or that we are dealing with. And so it turns out that if we have that particular expression, we must have s squared plus as plus b being equal to 0, because if I take e to the st and multiply it by that polynomial that's equal to 0, then clearly I get 0. Or, of course, another way to do it is to say that the other part of the product, specifically e to the st, is equal to 0. So we can go either one of those ways, at least, to get to 0. As you can imagine, though, we got a little bit of a problem, specifically with that second possibility, because e to the st can approach 0, but it can never be identically equal to 0. So as t goes to infinity, and if we have negative values of s, then sure enough, this e to the st can be approaching 0, but it can't identically get to 0. So that means that, of course, the only thing that makes sense is to have the characteristic equation itself. Oh, and I just kind of spilled the beans. The polynomial that's set equal to 0, there we go, that's another way to say it. That one has to be equal to 0. That's the only way to drive this to 0. But don't worry, I didn't spoil it for long. So that's the only way this, we can just go with the equation can be valid. This means, of course, that the nature or the character of the system response, here I'll just say of the response, is then driven by s squared plus as plus b equals 0. And s I already spoiled for you. This particular equation, since it determines the character of the response, is called the characteristic equation for the differential equation for this LTI ODE. So clearly, though, since we're dealing with an s squared, if we want to find the values of s that make this equation true, because right now we just have values of s, and not every value of s will satisfy that equation. So if we want to find the values of s that satisfy the equation, and since we're dealing with a squared, we just go ahead and use the quadratic formula. So then we can find s1 comma 2 is equal to negative a plus minus square root. And here I'm already capturing that the leading coefficient is going to be 1. A squared minus 4b over 2. Now we'll rewrite this particular quadratic equation or quadratic formula in a slightly different way a little bit later, because it'll be more convenient for us, but clearly this is what we're dealing with if we want to find those particular values of s that satisfy this equation. So as I said, the characteristic equation drives the general nature of the response. And so we can identify or further recognize that we end up, now that we have the quadratic formula coming into the mix, we can end up with 3 different cases that yield fundamentally different types of responses. Now, this leads to 3 cases, and those 3 cases are determined. So let's figure out how we can identify the fact that we have 3 cases. It's determined by the discriminant. Now, as you might remember, the discriminant is the quantity underneath the radical, underneath the square root, a squared minus 4b. So this particular quantity, the discriminant, and if you want to kind of remember it, you can say that the discriminant allows us to discriminate between these 3 different cases. I don't know if that's where this term discriminant came from long ago, but nonetheless, it does give us an interesting way of tying the fact that this discriminant is allowing us to figure out what's going on with, or which of these 3 particular cases we're dealing with. In other words, allowing us to discriminate between those 3 different cases. So you might still be thinking though, well, Professor Dinsmore, that's great. You still haven't explained the 3 different cases. Well, let's go ahead and we'll break each of the cases down individually, but we have, and so here we'll have note. Whoa, there we go. That looks a little bit better. So the first thing that I will note is that the discriminant in here, I'll just do this as DISC. The discriminant can be greater than 0. In which case then we have positive values of the discriminant, and then I can take the square root of positive values of the discriminant without any problem. And so then I have a negative a plus minus, and here we're going to assume that all of our coefficients are real. So that's the first thing that we have to get out of the way. So we'll assume that all of our coefficients are real. So then we get a negative a, and by the way, for engineering systems, that's going to be the case. I don't think we've figured out ways to have imaginary coefficients yet for real systems. So then we get a negative a, which is a real number, plus minus square root of another real number. And so then we end up with clearly real numbers in the numerator, and we have a real number in the denominator, and we're just dealing with real roots. The second possible case is where the discriminant is equal to 0, in which case then we have still real roots, but now the real roots are repeated, because when I add 0 to something, I end up with the same number. When I subtract 0 from something, I end up with the same number, and so both of my roots are the same. And so that's another case that we need to look at. So we need to look at the case when we have positive real values for the discriminant, the case when the discriminant is equal to 0, and then of course, all of our favorite cases when the discriminant is negative, in which case we're dealing with a real number, negative a, plus or minus now a purely imaginary number that comes from taking the square root of a negative number. So we of course strip off that negative and then just take the square root of the positive version of the number, and then we deal with that negative sign in a slightly different way. And we call those numbers complex numbers. So we have our three cases. We have the case where we have, and understand, remember the term root. The term root is specifically for a polynomial. The term root means the values of the variable that will give us a zero, that will yield a value of 0 when we substitute those values into the polynomial. So remember, that's the definition of the root. So here we can see that S really is giving us the roots of the characteristic equation, and those roots can, again, either be positive real roots, non-repeated, so positive distinct real roots, repeated real roots, or complex roots. Now, there, of course, is a case where we can have repeated purely imaginary roots. That's another possibility. And so that's something else that we would need to look at. So that's another discussion that we really aren't going to get into in this class, but will probably be covered in your control theory class, your classical controls class. So understand that possibility does, of course, exist. And we could even go a little bit further and say, oh, it is possible to have repeated complex roots as well. Though, as you'll see, there are special concerns associated with repeated purely imaginary roots when you get to control theory. Repeated purely imaginary roots that aren't really quite as much of a concern when we're dealing with repeated real components. So with that said, let's go ahead then and start focusing. So you now have a little bit of a better understanding, because you can see there are three different cases right there. I've thrown in a fourth case that we won't really discuss in this particular class. So let's go ahead and start marching through these three different cases. So let's start with probably what is conceptually the easiest case. Of course, that's when the discriminant is positive. And so here we have a squared is greater than 4 times b, which of course means that the discriminant is greater than 0, and of course that means then that the quadratic equation yields what we call two distinct, because they will be different, they will have different values, because we can't take a positive real value and add it to a particular value and then take that positive real value and subtract it from that same value and end up with the same value. It just doesn't happen. It would have to be 0 to get those repeated roots, as we've already discussed. So we get distinct, what are called distinct real roots. So I'm going to rewrite, though, this expression, and even though it isn't quite as helpful at this point in the discussion, it will certainly be helpful when we start talking about specifically case 3, which is where we're dealing with complex roots. So here I'm just going to take that 1/2, and instead of just having it as a 2 in the denominator, I'm going to explicitly multiply both terms of the numerator by that 1/2. And so again, this is going to make the form a little bit easier later on. So again, we have a particular quantity. If I have a non-zero quantity over here and I add it to that particular quantity and then subtract it from that particular quantity, we're going to end up with two different values. So now let's go ahead. Now remember, both of these are roots of the characteristic equation. And so these are values that will solve or help us solve the differential equation. So remember, we had an assumed form for the solution. So let's first substitute those back into the assumed form for the solution. And here I'll just shorten down solution. And so remember, we're dealing with the homogeneous case. This is going to be important because when we start talking about non-homogeneous cases, we're going to have to make the solution space a little bit more complicated, a little bit more complex. So we get XH1, our first homogeneous solution. The function associated with our first homogeneous solution is equal to e to the S1t. So remember, we assumed a solution e to the st. Now we have S1 and S2. So our first solution will be e to the S1t. And our second function that will solve this differential equation is e to the S2t. So we'll call that XH2, the second homogeneous solution for this differential equation. Now, and here let's just kind of do this in a different color because we'll have this S and a side. Let's do it in green. That looks a little alarming there as this orange kind of thing. Okay, so let's go ahead and have a little aside. So this just kind of helps you understand things. This discussion is to help you understand things. We could just jump to the final result, which is what I did in my notes. But I think it's valuable to discuss this because understanding that XH1 is a solution, then what does that mean? Well, that means that if I have XH1 double dot plus A XH1 dot plus B XH1, if that XH1 is a solution, that has to give me 0. Right? That's it wouldn't be a solution otherwise. Now we can say the same thing about XH2. If that is a solution, then we get XH2 double dot plus AXH1. We're on 2 now. We're on 2, not 1. Of course, my eraser isn't working anymore. XH2, come on, give me a 2, give me a 2, dot. There we go, plus BXH2. And obviously, if that's a solution, that has to be equal to 0 as well. So let me ask you, if I have 0 and I say 0 is equal to 0, but I want to add something to this 0, well, can't I add 0 to 0 to get 0? And I mean, this seems like an absolutely silly question to ask, but the answer is obviously, yeah, sure. Why not? Okay, well, if that's the case, can't I have my first 0 be XH1 double dot plus AXH1 dot plus BXH1? Well, yeah, that's 0 for this homogeneous case. And then how about XH2 double dot? For my second 0, BXH2 dot, or sorry, A XH2 dot, and B times XH2. Well, that's 0. So aren't I just adding 0 to 0? And the answer is, yeah, of course I am. And of course, that's going to lead to a value. When I add everything together, that's going to give me another 0. So then we can see, if I go ahead and start factoring things out here, I get an XH1 dot plus an XH1 double dot plus an XH2 double dot plus a XH1 dot plus XH2 dot plus B XH1 plus XH2. Well, clearly that's equal to 0. I haven't changed anything. But this is the original differential equation. The only thing I've substituted in now, instead of XH1 or XH2 and their appropriate derivatives, I've now substituted in the sum. So what does that mean? That means that a sum of the homogeneous solutions is another solution for this differential equation, or for this, more generally, for this specific class of differential equations. Oh, wait, but things get even more interesting, because what happens if I add 0 to 0, but then I go even one step further and say, okay, but what happens if I take C1 and multiply that by 0, and I take C2 and I multiply that by 0? Don't I still get 0? And of course, the answer is, yeah, of course you do. So then what does that mean? That means that it's not just a sum of XH1, a sum of the homogeneous solutions, XH1 and XH2, that solves the differential equation. It also turns out that I can scale those individual functions by any constant, and I get another solution. So that means that I have C1 times XH1 double dot plus AXH1 dot plus BXH1 plus C2 times XH2 double dot plus AXH2 dot plus BXH2, though that looks more like 2 H's rather than an H2. Okay, so let's get that adjusted here. There we go. And so, of course, if I distribute the C's on across and then collect up the terms, just like I did up above, what do I get? I get C1 XH1 double dot plus C2 XH2 double dot plus A C1 XH1 dot plus C2 XH2 dot plus B times the quantity XH1. Ooh, sorry about that. And I even forgot to put my C's in there. So definitely missed on 2 accounts. Okay, so then I have, come on, C1 times XH1 plus C2 XH2, and that's clearly equal to 0, has to be. And of course, the whole point here is this is another solution, because of course when I take the first derivative I end up with this, and I take the second derivative I end up with that, and I substitute those derivatives, the original combination and the derivatives of those combinations, in for the appropriate derivatives. I get another solution to this homogeneous differential equation. So, and that's because because it is a homogeneous, that's the key here, is it's a homogeneous differential equation. We keep getting zeros, right? That wouldn't be generally true, and it's not true with non-homogeneous differential equations. We'll see though that there is something in there where we still have this homogeneous contribution to the solution associated with a non-homogeneous differential equation, because again, we still get zeros. But the key here is that we keep getting zeros for these different solutions because we're dealing with the homogeneous case, and that allows us to develop more general solutions for this differential equation than we would just get if we were just playing with this xh1 and this xh2 by themselves. So let's go ahead and summarize all of that, because we can then say, so we'll go back to our black pen here to say, okay, we're resuming this lecture. Actually, let me go back to the green pen for 1 second so that I can go ahead and say that this is our aside here, convincing you that, of course, we can not only work with the individual solutions, but we can add those solutions, and even more generally, we can add those solutions that are scaled, those solutions after we've scaled those solutions by different constants, or generally different constants. So we can capture that idea by saying, so remember, when I take different constants and multiply things by them and then add those products together of constants times whatever we're multiplying, in this case homogeneous solutions, we end up with what's called a linear combination. So it turns out that a linear combination, as I've just shown you, of these homogeneous solutions is also a solution, because of course I can form that linear combination, take the appropriate derivatives, substitute it into the differential equation, and sure enough, the differential equation is satisfied. So we can then say that the most general form of the solution, where x is the solution for this differential equation, is c1 times xh1 plus c2 times xh2, which of course for us, if we want to substitute it in, is c1 e to the s1t plus c2 e to the s2t. And here we'll capture that the fact that C1 and C2 can be any constants. And here I won't levy the same restrictions, and as you'll see, it becomes convenient later on. I won't levy the same restrictions that C1 and C2 must be real. But for right now, we don't need to worry about the fact that they could be complex or purely imaginary if we chose them to be. So these are arbitrary constants, and these constants are determined by the initial conditions associated with whatever problem we are trying to solve. And initial conditions, will call those ICs because that's happening in time, so it would be an initial point in time. If it happens at a particular point in space, we usually call that a boundary condition, a BC. I think the text calls problems associated with that boundary value problems. So that gives you an understanding. So if it's an initial, quote unquote, an initial point in space, i.e. a boundary, then we call it a boundary condition. If it's an initial point in time, which is what we're generally dealing with for most engineering applications, that we do that we do deal with boundary conditions as well. But for a lot of times we're trying, in a lot of cases we're trying to figure out how something evolves in time rather than how something, if you want to call it that, evolves in space. And so we're going to be dealing an awful lot with initial conditions, as well as in some cases boundary conditions. So when we're looking at this, we can now see that we have the most general, solution to the differential equation. Because if I wanted each homogeneous solution individually, I would just go ahead and set one of the constants to 0 and the other one to 1. And then I have the individual unscaled form of our initial solution, or our homogeneous solution, I should say. And then if I wanted the other one, I'd just switch which constant set equal to 0 and which constant set equal to 1. Additionally, since we are dealing with real roots, one of the things that we can also see is that we have what we call an exponential response associated with this particular system. So remember, I indicated that the characteristic equation gives us an understanding of the character of the response. Well, for a value of a discriminant that's greater than 0, we get positive real roots, or sorry, I shouldn't say positive, we get real roots, hopefully not all positive. We get real roots, and those real roots are going to do what? They are going to give us exponential responses. So notice real roots, distinct. Let's actually be even a little bit more precise there. Distinct real roots generate an exponential response. Now, we can drill down even a little bit more, and this is important for us as engineers. Don't know why my pen just stopped writing there. This is very important for us as engineers, that if either S1 and or, so I'll use either, but it can be and or, S2 are positive, the solution has exponential growth associated with it. Now, if, on the other hand, both S1 and, so this is a stricter requirement, S1 and S2 are negative, the solution will exhibit exponential decay. And why is that important for us? Because we as engineers generally cannot tolerate systems that have exponential growth associated with their response. We will generally call, well, more than generally, when you get into controls, and I might even use it more than once in this class, when you have what's called a bounded input, and that bounded input will be associated with our non-homogeneous cases. When we have a bounded input, but we get an unbounded output where exponential growth is clearly an unbounded output, we will call those types of systems unstable systems that yield that kind of unbounded output for a bounded input. Now understand that there's only one way that we can get that unbounded output when we have constrained our input to be bounded, which is the fact that the system has these positive real roots. That's the only way it can happen, and it's a system argument, not an input argument, not an argument associated with what we have for our non-homogeneous side of the equation. It's the system that will drive the response unstable. And so for us to have a stable response, that means that we cannot have the real components of any of our roots being positive. We can't have it, because so in other words, they have to be negative or just purely imaginary. So zero, or the real components either have to be zero or they have to be negative in order for us to have what we would consider a stable system based on how I've described a stable system just now, where we have a bounded output for a bounded input. If you have positive values for those real components of the roots, you will have an unbounded output and the system will be unstable. Now, there are other definitions of stability that we're not going to get into in this class. We're just going to keep it really basic, but that is essentially the easiest way to think about stability. You get, for an unstable system, you get an unbounded output for a bounded input. For a stable system, you get a bounded output for a bounded input. And we can see exactly what happens with negative values of the roots associated with a characteristic equation, that you can even envision that more than just being bounded, that output will eventually decay to zero in almost all cases, with the exception of where the where the real component is equal to zero. And at that point, we're even kind of a little scared. So for almost all engineering systems, we have one of two cases. It is possible to have a purely oscillatory case that does nothing but oscillate forever and ever and ever, which is a bounded output. But you are so close to being unstable that generally, as engineers, we do not design for that case. So we generally end up with one of two cases. We either have a stable system where the system response decays toward a specific constant value. The transient response decays toward a specific constant value. Or we have a system whose output grows without bound, with a bounded input, grows without bound, and we call that an unstable system. So hopefully you're kind of now starting to get an idea of how these roots associated with the characteristic equation are so important for us and how the system is going to respond. So please understand that even though in this class we're kind of still taking more the mathy approach to things and talking about things in an abstract way where positive values of the real component of a root those are perfectly fine, just as fine as negative values. From an engineering perspective, you can hopefully start to see, oh no, negative values are what we're looking for the real components of those roots, and positive values are flashing warning signs and raising warning flags left and right. If you have positive real components, that's usually a sign that we have a real problem. Okay, so take that information, kind of put it in your head. Kreisig really doesn't make as big of a deal or the text, I should say, doesn't make as big of a deal about it as I'm making, but that's because the mathematicians aren't quite as worried generally about it as we are as engineers, whether or not we have bounded or unbounded outputs. So just please make a note of that. I'll mention it a few times during this class, but that will become a much bigger deal when you start getting into control theory itself. Now, one thing that I want to address, one point that I want to make, is we have these constants, C1 and C2. And you might be thinking, well, that's nice that they're two constants, but I want you to understand that it is an absolute necessity that we have these two constants. And let's see why. Now, there's a couple different ways that we can look at it. Here we just saw that these two constants just naturally came out of the development associated with this solution for the differential equation. But I want to make it a bit more plain that we had to end up with, in general, two constants. Now, of course, one of the constants we could find that it ends up being 0 if we're dealing with a particular degenerate case associated with the initial conditions. And so that could be the case. But generally, we will have two non-zero constants associated with the solution. So here I'll just say that it makes sense that there would be two constants. Because let's say, here we're working with X, but let's say that instead we were actually working with, because we could choose to target either the function itself or one of the derivatives. Let's say that we actually knew the second derivative of X. Let's say we actually found the second derivative of X rather than working with X itself. And if that was the case and we wanted to find X, because generally that's what we're interested in, we would, of course, get two constants of integration. Again, these constants of integration would also be determined by the initial conditions or boundary conditions, depending on which case you're working with. So let's go ahead and take a look at that. So we're going to assume that we know the function, completely know the function associated with the second derivative. So then, of course, to find the first derivative, because our differential equation has not only the second derivative, it also has the first derivative as well as the function itself. So that would be the integral of d squared x dt squared times dt, and here I'll explicitly pull out the constant of integration associated with that indefinite integral. Additionally, we would see that x is just the integral of this dx dt, which is just the integral of d squared x dt squared times dt plus c prime times dt. But again, I can explicitly pull out the constant of integration associated with this second indefinite integral. And so then we can see, because we can integrate each of these terms individually, and obviously the integral associated with the second term is quite simple, we can see then pretty quickly that we get our second integral, the second integral of d squared x dt squared times dt times another dt plus, and then going ahead and integrating the second one, I'm simply going to get a c prime times t plus ac triple prime, because of course I'm going to get a constant of integration from here, but from that integral, but I can go ahead and combine that constant of integration with our c double prime and end up with c triple prime. So now going ahead and substituting all of this back into the differential equation, so I'll say this as plugging back into the diffEq, differential equation, then we get d squared x dt squared plus, then we have our a times our integral d squared x dt squared dt, and here let's just go ahead and put this in parentheses so that I can add in my c prime, plus then b times, let's put that down on a lower line actually. Plus b times then our integral of d squared x dt squared dt times dt plus c prime t plus c triple prime. And of course, all this still has to be equal to 0. Now, clearly, though, I can start distributing the coefficients out, and I get a d squared x dt squared plus a times the integral d squared x dt squared dt plus a times c prime plus a b times the double integral of the integral d squared x dt squared dt plus a b times c prime t plus a b times c triple prime. There we go, that looks a little bit better. And that's equal to 0. But clearly, I can go ahead and combine these together, because these are just two constants added together, and that's just going to give me another constant. Here I have two constants multiplied together, so that's going to give me, again, another constant. And so then I can say that we have d squared x dt squared plus a times the integral d squared x dt times dt, forgot my squared there, plus then b times the integral of the integral. Now let me make that more integral-y. Yep, eraser, come up. There we go. So then we have integral, come on. I don't know why it's not taking, be good, pen. Integral d squared x dt squared dt, all that times dt, plus then a c1 times t plus c2 is equal to 0. And so sure enough, we can see that no matter how we approach the solution, we have two constants of integration, or two constants, let's say it that way, two constants that we need to be dealing with. And there's no way around it. So that gives us an understanding that this idea of two constants appearing in this, let's go all the way back up here, the two constants appearing, there we are, in this particular general, or this specific general solution, that wasn't arbitrary. You had to have two constants, and we can see why that would have to be the case looking at finding the solution in a slightly different way. So hopefully that gives you a bit of a better understanding that we don't just arbitrarily have two constants, we have to have two constants. So that's going to become a very important argument here in just a second. So we've now looked at case one, where we have distinct real roots. And we saw that when we found the homogeneous solutions, that we could also take, and it was we ended up with the most general solution by forming, let's not say taking, but by forming a linear combination of those homogeneous solutions. And then we saw that that most general solution has two constants associated with it, the values of those constants as far as the homogeneous form of the equation is concerned. The values of those two constants are arbitrary, but the fact that we have two constants certainly was not arbitrary. We have a second order differential equation. We have two constants. So now let's look at case two, and I already kind of spoiled what case two is all about. This is where a squared is equal to 4b, so the discriminant is now 0. And so, of course, when we look at the quadratic equation, of course, will yield two repeated roots, real roots. I need to squeeze that in there. So two repeated real roots. And so going ahead and representing that in, oh, come on, eraser, be good. Representing that using the specific form of the quadratic equation that I presented before for our case of two distinct real roots. We have our -1/2 times a plus minus then the quantity that involved the radical. Well, of course, and consequently the discriminant. And of course, we've now decided, or we're assuming that's 0. So then that means that our roots are just -1/2 times a for both S1 and S2, indicating that we're dealing with repeated. So remember, we're assuming a is constant, or sorry, a is real and constant. And so we end up with repeated real roots for that particular characteristic equation. So let's go ahead now, just to simplify things, and let's let S1 comma 2 be equal to S1, which is equal to S2, which is now just equal to SR for repeated real roots. So then, of course, substituting this back in, substituting this root, this repeated root, back into the general form, that we assumed for our solution, what do we then get? Well, we get xh1 is equal to e to the SRT. We get sh2, or xh2 is equal to e to the SRT. That's not looking terribly good. Well, let's kind of press forward, because remember, we can form a linear combination. And that linear combination is also a solution. And so thankfully, or at least you might be saying, Professor Dinsmore, that's so great. For some reason, my eraser isn't allowing me to erase. You might be like, Professor Dinsmore, that's great. That saves us, right? Because then we say, x is equal to c prime e to the SRT plus c double prime e to the SRT. And there we go. With the constants associated with the solution, we have two different terms, and we're good to go. And no, we're not. Because understand that these functions are not independent. Not only are they not independent, they are the same. So that means that really what I have is I have a c triple prime e to the SRT, and no, I only have, in reality, a single constant that's associated with the solution, no matter how you look at it. And so that means that what we can call our basis functions that we initially thought we had, those basis functions are not independent. And when I say basis, I mean that we are producing a solution by using these functions essentially as unit vectors, if you'd like to think about it that way. They're playing the same role as unit vectors for describing a vector. And so up here, what do we have? So remember, unit vectors, I hat, j hat, we want those to be independent unit vectors. Well, we need these functions to be independent functions if they are going to provide a basis for the solution. And how did you describe a vector when you were working with those kinds of quantities? Oh, well, each unit vector could be multiplied by its own constant. Look at that. And so we can see that these general homogeneous solutions are what? Are really just linear combinations of these basis functions, but the basis functions have to be independent. And when we have two real distinct roots, they are independent. There's no way that I can combine this guy together and get, through multiplying by constants or whatever, there's no way I can do it and get this guy. It's impossible. But when I come back down here, my basis functions are dependent because I can develop a quantity here that exactly eliminates that quantity there. I just choose negative C double prime for C prime, and it would always wipe it out, indicating that my two basis vectors are dependent on each other. Whereas up here, again, I can't choose. There's no way I can choose a C1, no matter what C2 is, there's no way I can choose a C1 that will allow me to take this quantity here and wipe out that quantity there for any value of time. That's the key. It has to be for, well, I shouldn't say any, for all values of time. I can't wipe it out. It just doesn't work. But down here, of course, I can. I can wipe one term out with the other term, indicating that those two, for any value of time, for every value of time, indicating that these two basis functions are dependent on each other. Not only are they dependent on each other, they're exactly the same. So clearly, I only end up with a single constant associated with this general form of the solution that I'm proposing based off of the roots associated with the characteristic equation. And so we got a problem, because as we just pointed out, as we were just discussing, for a second order differential equation, you need to have two constants to be able to properly capture what's happening with all of the initial or boundary conditions. There's just no way around it. So let's go ahead and capture that, because we clearly have a problem. So that means that this, but there is an issue. This is just capturing that as second order system. So this second order system will have, or I should say possibly will have, but generally will have. Let's put the generally in there. I don't want to. Two initial conditions. And here I'm kind of showing my bias because I'm saying that 0 isn't an initial condition, which it really is. But I just want to make sure that you understand that in pretty much all cases, we're going to have two initial conditions, whether they be 0 or otherwise. So we have two initial conditions, but we only have one constant. Which of course is doing what? This is indicating that, so when we see this, we know, ooh, we got a problem. This is really indicating that we haven't, this method that we're using of assuming the solution hasn't given us the complete solution. We're still missing some kind of component, another component associated with the solution that would then give us that second constant that we know we need to have. So that's what this is screaming. Is it saying, hey, great, you found one solution or one component to the solution, but in this particular case where we have repeated real roots, this solution approach hasn't been able to identify the entire solution, both components associated with it. So that's what this is screaming. So let's go ahead and capture that this can't be. the complete solution. We know it's incomplete because it's not able. Oh, sorry about that. Well, looks like I lost my session there, so I'm just going to go ahead and stop recording. And I'll go ahead and pick up with another session here in a second.